This presentation is delivered by the Stanford Center for Professional Development.
Okay, good morning. Welcome to CS229, the machine learning class. So what I want to do today is just spend a lot of time going over the logistics for the class, and then we'll start to talk a bit about machine learning. By way of introduction, my name is Andrew and I'll be instructor for this class. And so I personally work in machine learning, and I've worked on it for about 15 years now. And I actually think that machine learning is the most exciting field of all of computer science. So I'm actually always excited about teaching this class. Sometimes I actually think that machine learning is not only the most exciting thing in computer science, but the most exciting thing in all of human endeavor. So maybe a little bias there. Also want to introduce the TAs, who are all graduate students doing research in or related to machine learning and all experts in machine learning. Paul Baumstock works in machine learning and computer vision. Katie Chang is actually a neuroscientist who applies machine learning algorithms to try to understand the human brain. Tom Doe is another PhD student, works in computational biology and in sort of the basics, fundamentals of machine learning. Zico Coulter is the head TA. He's head TA 2 years in a row now. Works on machine learning and applies them to a bunch of robots. And Daniel Ramage is, because it's not here, Daniel applies learning algorithms to problems in natural language processing. So you get to know the TAs and me much better throughout this quarter. But just from, the sorts of things that TAs do, I hope you can already tell that machine learning is a highly interdisciplinary topic in which just the TAs are applying learning algorithms to problems in computer vision, in biology, in robots, in language. And machine learning is one of those things that has had and is having a large impact on many applications. So just in my own daily work, I actually frequently end up talking to people like helicopter pilots, to biologists, to people in computer systems or databases, to economists, and there's sort of also an unending stream of people from industry coming to Stanford, interested in applying machine learning problems, interested in applying machine learning methods to their own problems. So yeah, this is fun. A couple of weeks ago, a student actually forwarded to me an article on in Computer World about the 12 IT skills that employers can't say no to. Sort of about the sort of the 12 most desirable skills in all of IT and all of information technology. And topping the list was actually machine learning. So I think this is a good time to be learning this stuff, and learning algorithms are having a large impact on many segments of science and industry. I'm actually curious about something. Learning algorithms is one of the things that touches many areas of science and industries. I'm actually kind of curious, how many people here are computer science majors or in the computer science department? Okay, about half of you. How many people are from EE? Oh, okay, maybe about a fifth. How many biologists are there here? Wow, just a few, not many. I'm surprised. Anyone from statistics? Okay, a few. Ooh, so where are the rest of you from? What, say again? ICME, cool. Civi and what else? Simsys, Convex Systems, yeah, cool. Chemi, cool. Aeroastro, yes, right. Yeah, okay, cool. Anyone else? Yeah. Pardon? MSNE. All right, cool, yeah. So, pardon? Endoship. What's industry. Okay, cool, right, great. Yeah, so as you can tell, from the cross-section of this class, I think we're a very diverse audience in this room, and that's one of the things that makes this class fun to teach and fun to be in, I think. So in this class, we try to convey to you a broad set of principles and tools that will be useful for doing many, many things. And every time I teach this class, I can actually very confidently say that after December, no matter what you go on to do after this December, when you've sort of completed this class, you'll find the things you learn in this class very useful. And these things will be useful pretty much no matter what you end up doing later in your life. So I have more logistics to go over later, but let's say a few more words about machine learning. I feel that machine learning grew out of early work in AI, early work in artificial intelligence. And over the last, I want to say, over the last 20 years or so, it's been viewed as a sort of growing new capability for computers. And in particular, it turns out that there are many programs, or there are many applications that you can't program by hand. For example, if you want to get a computer to read handwritten characters, to read sort of handwritten digits, it actually turns out to be amazingly difficult to write a piece of software to take as input an image of something that I wrote and to figure out, just what it is, to translate my cursive handwriting into to extract the characters that I wrote out in longhand. And other things. One thing that my students and I do is autonomous flight. So it turns out to be extremely difficult to sit down and write a program to fly a helicopter. But in contrast, if you want to do things like these, to get software to fly a helicopter, have software recognize handwritten digits, one very successful approach is to use a learning algorithm and have a computer learn by itself how to, say, recognize your handwriting. And in fact, for handwritten digit recognition, this is pretty much the only approach that works well. And these are sort of applications that are hard to program by hand. Learning algorithms has also made, I guess, significant inroads in what's sometimes called database mining. So for example, with the growth of IT and computers, increasingly many hospitals are keeping around medical records of what sort of patients, what problems they had, what their prognosis was, what the outcome was. And taking all of these medical records, which started to be digitized only about maybe 15 years ago, applying learning algorithms to them, we can turn raw medical records into what I might loosely call medical knowledge, in which we start to detect trends in medical practice and even start to alter medical practice as a result of medical knowledge that's derived by applying learning algorithms to the source of medical records that hospitals have just been building up over the last 15, 20 years in electronic format. Turns out that most of you probably use learning algorithms, I don't know, I think half a dozen times a day or maybe a dozen times a day or more, and often without knowing it. So for example, every time you send mail via the US postal system, turns out there's an algorithm that tries to automatically read the zip code you wrote on your envelope, and that's done via a learning algorithm. So every time you send US mail, you're using a learning algorithm, perhaps without even being aware of it. Similarly, every time you write a check, I actually don't know the number for this, but a significant fraction of checks that you write are processed by a learning algorithm that's learned to read the digits, so the dollar amount that you wrote down on your check. So every time you write a check, there's another little learning algorithm that you're probably using without even being aware of it. If you use a credit card, or I know at least one phone company was doing this, and lots of companies like eBay as well that do electronic transactions, there's a good chance that there's a learning algorithm in the back end trying to figure out if, say, your credit card's been stolen or if someone's engaging in a fraudulent transaction. If you use a website like Amazon or Netflix that will often recommend books for you to buy or movies for you to rent or whatever, these are other examples of learning algorithms that have learned what sorts of things you like to buy, what sorts of movies you like to watch, and can therefore give customized recommendations to you. I don't know, just about a week ago I had my car service, and even there my car mechanic was trying to explain to me some learning algorithm and the innards of my car that's sort of doing its best to optimize my driving performance or fuel efficiency or something. So most of us use learning algorithms, half a dozen, maybe dozens of times without even knowing it. And of course, learning algorithms also doing things like giving us a growing understanding of the human genome. So if someday we ever find a cure for cancer, I bet learning algorithms will have had a large role in that. That's sort of the thing that Tom works on, yes. So in teaching this class, I sort of have 3 goals. One of them is just to help convey some of my own excitement about machine learning to you. The second goal is, by the end of this class, I hope all of you will be able to apply state-of-the-art machine learning algorithms to whatever problems you're interested in. And if you ever need to build a system for reading zip codes, you know how to do that by the end of this class. And lastly, by the end of this class, I realized that only a subset of you are interested in doing research in machine learning. But by the conclusion of this class, I hope that all of you will actually be well qualified to start doing research in machine learning. Okay. So let's say a few words about logistics. The prerequisites of this class are written on one of the handouts, are as follows. In this class, I'm going to assume that all of you have sort of basic knowledge of computer science and basic knowledge of the basic computer skills and principles. So I'll assume all of you know what big O notation is, that all of you know about sort of data structures like queues, stacks, binary trees, and that all of you know enough programming skills to write a simple computer program. And it turns out that most of this class will not be very programming intensive, although we will do some programming mostly in either MATLAB or Octave. I'll say a bit more about that later. Also assume familiarity with basic probability and statistics. So most undergraduate statistics class, like Stat 116 taught here at Stanford, will be more than enough. I'm going to assume that all of you know what random variables are, that all of you know what expectation is, what the variance of a random variable is. And if, in case for some of you, it's been a while since you've seen some of this material, at some of the discussion sections, we'll actually go over some of the prerequisites, sort of as a refresher course on the prerequisite class. And I'll say a bit more about that later as well. Lastly, I also assume familiarity with basic linear algebra. And again, most undergraduate linear algebra classes are more than enough. So if you've taken classes like Math 51, 103, Math 113, or CS 205 at Stanford, that would be more than enough. But basically, I'm going to assume that all of you know what matrices and vectors are, that you know how to multiply matrices and vectors, or multiply matrices and matrices, that you know what a matrix inverse is. If you know what an eigenvector of a matrix is, that'd be even better. But if you don't quite know, if you're not quite sure, that's fine too. We'll go over it in the review sections. Okay. So, there are a couple more logistical things I should deal with in this class. One is that, as most of you know, CS 229 is a televised class. In fact, I guess many of you are probably watching this, at home on TV. So I'm going to say hi to our home viewers. So earlier this year, I approached SCPD, which televises these classes, about trying to make a small number of Stanford classes publicly available, of posting the videos on the web. And so this year, Stanford is actually starting a small pilot program in which we'll post videos of a small number of classes online, sort of on the internet, in a way that makes it publicly accessible to everyone. I'm very excited about that because machine learning is cool. Let's get the word out there. One of the consequences of this is that, let's see, so videos or pictures of the students in this classroom will not be posted online. So your images, so don't worry about being surprised by seeing your own face appear on YouTube one day. But the microphones may pick up your voices. So I guess the consequence of that is that, because microphones may pick up your voices, no matter how irritated you are at me, don't yell out swear words in the middle of class. But because there won't be video, you can safely sit there and make faces at me, and that won't be shown. Okay. Let's see. I also handed out this. There were two handouts I hope most of you have. Course information handout. So let me just say a few words about parts of these. On the third page, there's a section that says online resources. Yeah. Oh, okay. Oh, louder?
Yeah.
Okay. Actually, could you turn up the volume? Testing. Is this better? Testing. Okay, cool. Thanks. So, right, online resources. The course is the homepage. It's written on the handouts. I won't write on the chalkboard. http cs229.stanford.edu. And so when there are homework assignments or things like that, we usually won't bring, so if, in the mission of saving trees, we will usually not give out many handouts in class. So homework assignments, homework solutions will be posted online at the course homepage. As part of this class, I've also written, and I guess I'm also revised every year, a set of fairly detailed lecture notes that cover the technical content of this class. And so if you go to the course homepage, you also find the detailed lecture notes that sort of cover, that go over in detail all the math and equations and so on that I'll be doing in class. There's also a news group, su.class.cs229, also written on the handout. This is a news group that's sort of a forum for people in the class to get to know each other and have whatever discussions you want to have amongst yourself. So the class news group will not be monitored by the TAs and me, but this is a place for you to form study groups or find project partners or discuss homework problems and so on, and it's not monitored by the TAs and me. So you can also, feel free to talk trash about this class there. If you want to contact the teaching staff, please use the email address written down here, cs229-qa@cs.stanford.edu. This goes to an account that's read by all the TAs and me. So rather than sending us email individually, if you send email to this account, it'll actually let us get back to you, maximally quickly with answers to your questions. If you're asking questions about homework problems, please say in the subject line which assignment and which question the email refers to, since that will also help us to route your question to the appropriate TA or to me appropriately and get the response back to you quickly. Let's see, skipping ahead, let's see, 4 homeworks, 1 midterm, 1 open-ended term project. Notes on the honor code. So one thing that I think will help you to succeed and do well in this class and even help you to enjoy this class more is if you form a study group. So maybe start looking around where you're sitting now, and at the end of class today, mingle a little bit and get to know your classmates. I strongly encourage you to form study groups and sort of have a group of people to study with and have a group of your fellow students to talk over these concepts with. You can also post on the class news group if you want to use that to try to form a study group. But some of the problem sets on this in this class are reasonably difficult. People that have taken class before may tell you they were very difficult. And just I think I'll bet it'll be more fun for you, and you probably have a better learning experience if you have if you form a study group of people to work with. So I definitely encourage you to do that. And just say a word on the honor code, which is that I definitely encourage you to form a study group and work together, discuss homework problems together. But if you discuss homework problems with other students, then I'll ask you to sort of go home and write down your own solutions independently without referring to notes that were taken in any of your joint study sessions. So in other words, when you turn in a homework problem, what you turn in should be something that was reconstructed, independently by yourself and without referring to notes that you took during your study sessions with other people. Okay, and obviously, showing your solution to others or copying other solutions directly is right out. We occasionally also reuse problem set questions from previous years so that the problems are a bit more debugged and work more smoothly. And as a result of that, I also ask you not to look at solutions from previous years. And this includes both sort of official solutions that we've given out to previous generations of this class and previous solutions that people that have taken this class in previous years may have written out by themselves. Okay. Sadly, in this class, there are usually, sadly in previous years, there have often been a few honor code violations in this class. And last year, I think I prosecuted 5 honor code violations, which I think is a ridiculously large number. And so just don't look at those solutions, and hopefully there'll be 0 honor code violations this year. I'd love for that to happen. There's a section here on the late homework policy. If you ever want to hand in the homework late, I'll leave you to read that yourself. We also have a midterm, which is scheduled for the Thursday, 8th of November at 6 p.m. So please keep that. Evening free. And let's see. And one more administrative thing I want to say is about the class project. So part of the goal of this class is to leave you well equipped to apply machine learning algorithms to a problem or to do research in machine learning. And so as part of this class, I'll ask you to execute a small research project, so as a small term project. And what most students do for this is either apply machine learning to a problem that you find interesting, or investigate some aspect of machine learning. So to those of you that are either already doing research, or to those of you who are in industry, or taking this from a company, one fantastic sort of way to do a class project would be if you apply machine learning algorithms to a problem that you're interested in, to a problem that you're already working on, whether it be a science research problem or sort of a problem in industry, you're trying to get a system to work using a learning algorithm. To those of you that are not currently doing research, one great way to do a project would be if you apply learning algorithms to just pick a problem that you care about, pick a problem that you find interesting, and apply learning algorithms to that and play with the ideas and see what happens. And let's see. And the goal of the project should really be for you to do a publishable piece of research in machine learning. Okay? And if you go to the course website, you actually find a list of the projects that students had done last year. And so I'm holding a list in my hand. You can go home later and take a look at it online. But reading down this list, I see that last year there were students that applied learning algorithms to control a snake robot. There was a few projects on improving learning algorithms. There's a project on flying autonomous aircraft. There was a project actually done by our TA Paul on improving computer vision algorithms using machine learning. There are a couple of projects on Netflix rankings using learning algorithms. A few medical robotics ones on segmenting IOTA, segmenting pieces of the body using learning algorithms. One on musical instrument detection, another on RNA sequence alignment. I don't know, few algorithms on understanding the brain, neuroscience, actually quite a few projects on neuroscience. Couple of projects on understanding fMRI data on brain scans, and so on. Another project on market making, so financial trading. There's an interesting project on trying to use learning algorithms to decide what is it that makes a person's face physically attractive. There's learning algorithm, optical illusions, and so on, and it goes on. So lots of fun projects. When you take a look, then come up with your own ideas, but whatever you find cool and interesting, I hope you'll be able to make a machine learning project out of it. Yeah, question?
Are these group projects?
Oh, yes, thank you.
So how many people can be in a group?
Right, so projects can be done in groups of up to 3 people. So as part of forming study groups, later today as you get to know your classmates, I definitely also encourage you to grab 2 other people and form a group of up to 3 people for your project. Okay, and just start brainstorming ideas for now amongst yourselves. You can also come talk to me or the TAs if you want to brainstorm ideas with us. Okay. So, one more organizational question. I'm curious, how many of you know MATLAB? Wow, cool, quite a lot. Okay, so as part of the actually, how many of you know Octave or have used Octave? Oh, okay, much smaller number. So, as part of this class, especially in the homeworks, we'll ask you to implement a few programs, a few machine learning algorithms as part of the homeworks. And most of those homeworks will be done in either MATLAB or in Octave, which is sort of a, I don't know, some people call it a free version of MATLAB, which is sort of isn't. So I guess for those of you that haven't seen MATLAB before, and I know most of you have, MATLAB is a programming, I guess, a programming language that makes it very easy to write code using matrices, to write code for numerical routines, to move data around, to plot data. And it's sort of an extremely easy to learn tool to use for implementing a lot of learning algorithms. And for those of you, in case some of you want to work, on your own home computer or something, if you don't have a MATLAB license, for the purposes of this class, there's also, I should just write that down, it's MATLAB. There's also a software package called Octave that you can download for free off the internet. And it has, somewhat fewer features than MATLAB, but it's free, and for the purposes of this class, it'll work for just about everything. So actually, yeah, just a side comment for those of you that haven't seen MATLAB before, I guess. Once a colleague of mine at a different university, not at Stanford, actually teaches another machine learning class. He taught it for many years. So one day, he was in his office, and an old student of his from like 10 years ago came into his office, and he said, "Oh, professor, thank you so much for your machine learning class. I learned so much from it. There's this stuff that I learned in your class that I now use every day, and it's helped me make lots of money, and here's a picture of my big house." So my friend was very excited. He said, "Wow, that's great. I'm glad to hear this machine learning stuff is actually useful. So what was it that you learned? Was it the logistic regression? Was it the PCA? Was it the Bayesian networks? What was it that you learned that was so helpful?" And the student said, "Oh, it's the MATLAB." So for those of you that don't know MATLAB yet, I hope to do learn it. It's not hard, and we'll actually have a short MATLAB tutorial in one of the discussion sections for those of you that don't know it. Okay, the very last piece of logistical thing is the discussion sections. So discussion sections will be taught by the TAs, and attendance at discussion sections is optional, although they'll also be recorded and televised. And we'll use the discussion sections mainly for two things. For the next 2 or 3 weeks, we'll use the discussion sections to go over the prerequisites to this class, or if some of you haven't seen probability or statistics for a while, or linear algebra. We'll go over those in the discussion sections as a refresher for those of you that want one. Later in this quarter, we'll also use the discussion sections to go over extensions to the material that I'm teaching in the main lecture. So machine learning is a huge field, and there are a few extensions that we really want to teach but didn't have time in the main lectures for. So later this quarter, we'll use the discussion sections to talk about things like convex optimization, to talk a bit about hidden Markov models, which is a type of machine learning algorithm for modeling time series, and a few other things. So extensions to the materials that I'll be covering in the main lectures. And attendance at the discussion sections is optional. Okay. So that was all I had from logistics. Before I move on to start talking a bit about machine learning, let me check what questions you have. Yeah.
The reading courses, do you have to use MATLAB and Octave, or can we program in R or something like that? Probably prefer this.
Yeah, let's see, right. So I would, so the policy as a policy has been that you're welcome to use R, but I would strongly advise against it, mainly because in the last problem set, we actually supply some code that will run in MATLAB and Octave, but that would be somewhat difficult for you to translate, but that would be somewhat painful for you to translate into R yourself. So for the early assignments, if you want to submit a solution in R, that's fine, but I think MATLAB is actually totally worth learning. I know R and MATLAB, and I personally end up using MATLAB quite a bit more often for various reasons. Cool. Yeah.
For the term project, do you recommend a group of 2 or also?
So for the term project, you're welcome to do it in smaller groups of 3. You're welcome to do it by yourself or in groups of 2. Grading is the same regardless of the group size. So with a larger group, you probably, I recommend trying to form a team, but it's actually certainly fine to do it in a smaller group if you want. Yeah, question?
For the programming prerequisite, what language? C or?
So let's see. There is no C programming in this class other than any that you may choose to do yourself in your project. So all the homeworks can be done in MATLAB or Octave, and let's see, and I guess the programming prerequisites is more the ability to understand big O notation and and knowledge of what a data structure like a linked list or a queue or a binary tree is, more so than knowledge of C or Java specifically. Yeah.
Looking at the end semester project, I mean, what exactly will you be testing over there? What will the grading methodology be?
Of the project. Yeah. Let me answer that later. Let me in a couple of weeks I should give out a handout with sort of guidelines for the project. But I think for now we should think of the goal as being to do a cool piece of machine learning work that will let you experience the joys of machine learning firsthand, and really try to think about doing a publishable piece of work. So many students will try to build a cool machine learning application. That's probably the most common project. Some students will try to improve state-of-the-art machine learning. Some of those projects are also very successful, but so a bit harder to do. And there's also a smaller minority of students that will sometimes try to develop the theory of machine learning further. We try to prove theorems about machine learning. So they're usually great projects of all of those types, with applications of machine learning being the most common. Anything else? Okay, cool. So that was it with logistics. Let's talk about learning algorithms. So can I have the laptop display, please? Can I have the projector? Actually, could you lower the big screen? Cool. This is amazing customer service. Thank you.
Sorry. I'm trying to get it going, but it's not.
Oh, I see. Okay, cool. Okay, no, that's fine.
We have technicians working on it.
I see. Okay, that's cool. Thanks. Okay, big screen isn't working today, but I hope you can read things on the smaller screens out there. Actually, in case you're wondering, I think this room just got a new projector that I don't know, someone sent you an excited email. Was it just on Friday, saying we just got a new projector in this, and they said with a 4,000 to 1 something or other brightness ratio. I don't know. So someone was very excited about the new projector in this room, but I guess we'll see that in operation on Wednesday. Start by talking about what machine learning is. What is machine learning? Here's a. Actually, can you read the text up there? Can you raise your hand if the text on the small screens is legible? Oh, okay, cool. Mostly legible. Okay, so I just read it out. So, what is machine learning? Way back in about 1959, Arthur Samuel defined machine learning informally as the field of study that gives computers to learn. Field of study that gives computers the ability to learn without being explicitly programmed. So Arthur Samuel, way back in the history of machine learning, actually did something very cool, which was he wrote a checkers program which would play games of checkers against itself. And so because a computer can play thousands of games against itself relatively quickly, Arthur Samuel had his program play thousands of games against itself, and over time it would start to learn to recognize patterns which led to wins and patterns which led to losses. So over time it learned things like that, gee, if I get a lot of my pieces taken by the opponent, then I'm more likely to lose than win. Or gee, if I get my pieces into a certain position, then I'm especially likely to win rather than lose. And so over time, Arthur Samuel had a checkers program that would actually learn to play checkers by learning what are the board positions that tend to be associated with wins and what are the board positions that tend to be associated with losses. And way back in around 1959, the amazing thing about this was that his program actually learned to play checkers much better than Arthur Samuel himself could. Right? So even today, there are some people that say, well, computers can't do anything that they're not explicitly programmed to. And Arthur Samuel's checkers program was maybe the first I think, really convincing refutation of this claim. Namely, Arthur Samuel managed to write a checkers program that could play checkers much better than he personally could. And this is an instance of maybe computers learning to do things that they really were not programmed explicitly to. Here's a more recent or more modern, more formal definition of machine learning due to Tom Mitchell, who says that a well-posed learning problem is defined as follows. He says that a computer program is said to learn from an experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. Right? So not only is it a definition, it even rhymes. So, for example, in the case of checkers, the experience E that the program has would be the experience of playing lots of games of checkers against itself, say. The task T is the task of playing checkers, and the performance measure P will be something like the fraction of games it wins against a certain set of human opponents. And by this definition, we'll say that Arthur Samuel's checkers program has learned to play checkers. Okay? So, as an overview of what we're going to do in this class is sort of organized into 4 major sections. I'm going to talk about 4 major topics in this class, the first of which is supervised learning. So let me give you an example of that. So suppose you collect a data set of housing prices, and one of the TAs, Dan Ramage, actually collected a data set for me last week to use an example later. But suppose that you go to collect statistics about how much houses cost in a certain geographic area, and Dan, the TA, collected data from housing prices in Portland, Oregon. So what you can do is, let's say, plot the square footage of the house against the list price of the house, right? So you get, so collect data on a bunch of houses. Let's say you get a data set like this with houses of different sizes that, are listed for different amounts of money. Now, let's say that I'm trying to sell a house in the same area as Portland, Oregon, was where the data comes from. Let's say I have a house that's, this size in square footage. And I want an algorithm to tell me about how much should I expect my house to sell for. Okay? So there are lots of ways to do this. And some of you may have seen elements of what I'm about to say before. So one thing you could do is look at this data and maybe fit a straight line to it. And then, if this is my house, you may then look at the straight line and predict that my house is going to go for about that much money, right? And there are other decisions that you can make, which we'll talk about later, which is, well, what if I don't want to fit a straight line? Maybe I should fit a quadratic function to it. Maybe that fits the data a little bit better. You notice if you do that, the price of my house goes up a bit, so that'd be nice. And this sort of learning problem of learning to predict housing prices is an example of what's called a supervised learning problem. And the reason it's called supervised learning is because we're providing the algorithm a data set of a bunch of square footages, a bunch of housing sizes, and as well as the right answer of what the actual prices of a number of houses were. Right? And so we call this supervised learning because we're supervising the algorithm. Or in other words, we're giving the algorithm the, quote, right answer for a number of houses, and then we want the algorithm to learn the association between the inputs and the outputs and to sort of give us more of the right answers. Okay? It turns out this particular example that I drew here is an example of something called a regression problem. And the term regression refers to the fact that the variable you're trying to predict is a continuous value, is a continuous valued price. Well, there's another class of supervised learning problems which we'll talk about, which are classification problems. And so in a classification problem, the variable you're trying to predict is discrete rather than continuous. So as one specific example that sort of actually a standard data set you can download online that I've worked on and that lots of machine learning people have played with. Let's say you collect a data set on breast cancer tumors, and you want to know, whether you want a learning algorithm to predict whether or not a certain tumor is malignant. Malignant is the opposite of benign, right? So malignant means it's a harmful, bad tumor. So we collect, some number of features, some number of properties of these tumors, and for the sake of, for the sake of sort of having a simple toy explanation, let's just say that we're going to look at the size of the tumor, and depending on the size of the tumor, we'll try to figure out whether or not the tumor is malignant or benign. So tumor is either malignant or benign, and so the variable on the y-axis is either 0 or 1, and so your data set may look like, may look something like that. Right? That's 1 and that's 0. Okay. And so this is an example of a classification problem where the variable you're trying to predict is discrete values, either 0 or 1. In fact, more generally, there'll be many learning problems where we'll have more than one input variable, more than one input feature, and use more than one variable to try to predict, say, whether a tumor is malignant or benign. So for example, continuing with this, you may instead have a data set that looks like this. I'm going to plot this data set in a slightly different way now. And I'm making this data set look much cleaner than it really is in reality for illustration. But okay, where, for example, maybe the crosses indicate malignant tumors, and the O's may indicate benign tumors. Right. And so you may have a data set comprising patients of different ages and who have different tumor sizes, and where a cross indicates a malignant tumor and an O indicates a benign tumor. And you may want an algorithm to learn to predict, given a new patient, whether their tumor is malignant or benign. Right? So for example, what a learning algorithm may do is maybe come in and decide that a straight line like that separates the two classes of tumors really well. And so if you have a new patient whose age and tumor size fall over there, then you may be, the algorithm may predict that the tumor is benign rather than malignant. Okay? So this is just another example of another supervised learning problem. And another classification problem. And so it turns out that one of the issues we'll talk about later in this class is in this specific example, we're going to try to predict whether a tumor is malignant or benign based on two features, or based on two inputs, namely the age of the patient and the tumor size. Turns out that when you look at real data sets, you find that learning algorithms often use other sets of features. In the breast cancer data example, you also use properties of the tumors like clump thickness, uniformity of cell size, uniformity of cell shape, marginal adhesion, and so on. So various other medical properties. And so, and one of the most interesting things we'll talk about later this quarter is what if your data doesn't lie in a two-dimensional or three-dimensional or sort of even a finite dimensional space? But is it possible, what if your data actually lies in an infinite dimensional space? Right? I plotted here a two-dimensional space. I can't plot to an infinite dimensional space, right? And so it turns out that one of the most successful classes of machine learning algorithms, something called support vector machines, actually takes data and works and maps data to an infinite dimensional space, and then does classification using not two features like I've done here, but an infinite number of features. And that will actually be one of the most fascinating things we talk about when we go deeply into classification algorithms. It's actually an interesting question, right? Is to think about how do you even represent an infinite dimensional vector, you know, in computer memory? You don't have an infinite amount of computers. How do you even represent a point that lies in infinite dimensional space? Right, we'll talk about that when we get to support vector machines. Okay. So let's see. Actually, I think. Well, so the second of the so that was supervised learning. The second of the 4 major topics of this class will be learning theory. So I have a friend who teaches math at a different university, not at Stanford. And when you talk to him about, you know, his work and what he's really out to do, this friend of mine will, so he's a math professor, right? This friend of mine will sort of get the look and wonder in his eyes, and he'll tell you about how in his mathematical work, he's, you know, he feels like he's discovering truth and beauty in the universe. And he says it in sort of a really touching, sincere way. And then he has this, you can see it in his eyes, there's this deep appreciation of, you know, the truth and beauty in the universe as revealed to him by the math he does. In this class, I'm not going to do any truth and beauty. In this class, I'm going to talk about learning theory to try to convey to you an understanding of how and why learning algorithms work, so that we can apply these learning algorithms as effectively as possible. So for example, it turns out you can prove surprisingly deep theorems on when you can guarantee that the learning algorithm will work. Right? So think about a learning algorithm for reading zip codes. When can you prove a theorem guaranteeing that the learning algorithm will be at least 99.9% accurate on reading zip codes? This is actually somewhat surprising. We actually prove theorems showing when you can expect that to hold. We'll also sort of delve into learning theory to try to understand what algorithms can approximate different functions well and when, and also try to understand things like how much training data do you need? So how many examples of houses do I need in order for your learning algorithm to recognize the pattern between, you know, the square footage of a house and its housing prices? And this is help us answer questions like, if you're trying to design a learning algorithm, should you be spending more time collecting more data? Or is it the case that you already have enough data and it'd be a waste of time to try to collect more? Okay, so I think learning algorithms are a very powerful tool, but as I, you know, walk around industry in Silicon Valley, or as I work with various students in CS and outside CS, you find that there's often a huge difference between how well someone who really understands this stuff can apply a learning algorithm versus someone who, you know, sort of gets it but sort of doesn't. The analogy I like to think of is think of if imagine you were going to, you know, carpentry school instead of a machine learning class, right? If you go to a carpentry school, they can give you the tools of carpentry. They give you a hammer, a bunch of nails, a screwdriver, or whatever. But a master carpenter will be able to use those tools far better than most of us in this room. So I know a carpenter can do things with a hammer and nail that I couldn't possibly. And it's actually a little bit like that in machine learning too. One thing that's sadly not taught in many courses on machine learning is how to take the tools of machine learning and really, really apply them well. So in the same way, so the tools of machine learning are, you know, I want to say quite a bit more advanced than the tools of carpentry. Maybe a carpenter will disagree. But so a large part of this class will be just giving you the raw tools of machine learning, just the algorithms and so on. But what I plan to do throughout this entire quarter, not just in the segment of learning theory, but actually as a theme running through everything I do this quarter, will be to try to convey to you the skills to really take the learning algorithm ideas and really to get them to work on the problem. It's sort of hard for me to, you know, stand here and say how big a deal that is. But when I walk around companies in Silicon Valley, it's completely not uncommon for me to see someone using some machine learning algorithm and then explain to me what they've been doing for the last 6 months. And I go, oh, gee, you know, it should have been obvious from the start that the last 6 months you've been wasting your time, right? So my goal in this class, running through the entire quarter, not just on learning theory, is actually not only to give you the tools of machine learning, but to teach you how to use them well. And I've noticed this is something that really not many other classes teach. So, this is something I'm really convinced is a huge deal. And so, by the end of this class, I hope all of you will be master carpenters. I hope all of you will be really good at applying these learning algorithms, and getting them to work amazingly well on many problems. Okay. Let's see. So, some of these slides out of the board. After learning theory, there's another class of learning algorithms that I then want to teach you about. And that's unsupervised learning. So, you recall, right? Well, on the a little earlier, I drew an example like this, right, where you have a couple of features, a couple of input variables, and sort of malignant tumors and benign tumors or whatever. And that was an example of a supervised learning problem because the data you have gives you the right answer for each of your patients. The data tells you this patient had a malignant tumor, this patient had a benign tumor. So it had the right answers, and you wanted the algorithm to just produce more of the same. In contrast, in an unsupervised learning problem, this is the sort of data you get. Okay. Where, speaking loosely, you're given a data set, and I'm not going to tell you what the right answer is on any of your data. I'm just going to give you a data set, and I'm going to say, would you please find interesting structure in this data for me? So that's the unsupervised learning problem, where you're sort of not given the right answer for everything. So for example, an algorithm may find structure in the data in the form of the data being partitioned into two clusters. So clustering would be one example of an unsupervised learning problem. So you can see this. It turns out that these sorts of unsupervised learning algorithms are also used for many problems. This is a screenshot. This is a picture I got from Sue Lee, who's a PhD student here, who's applying unsupervised learning algorithms to try to understand gene data. So, it's trying to look at genes in individuals and group them into clusters based on properties of what genes they respond to, based on properties of how the genes respond to different experiments. Another interesting application of these sorts of clustering algorithms is actually the image processing. This picture I got from Steve Gould, who's another PhD student. It turns out what you can do is if you give this sort of data, say an image, to certain unsupervised learning algorithms, they will then learn to group pixels together and say, gee, this set of pixels seem to belong together and that set of pixels seem to belong together. And so the images you see on the bottom, I guess you can just barely see them. So the images you see on the bottom are groupings, are what the algorithm has done to group different pixels together. On a small display, it might be easier to just look at the image on the right. The two images at the bottom are two sort of identical visualizations of the same grouping of the pixels into contiguous regions. And so it turns out that this sort of clustering algorithm, this sort of unsupervised learning algorithm, which sort of learns to group pixels together, it turns out to be useful for many applications in vision, in computer vision image processing. Let's show you one example. This is a rather cool one that two students, Ashutosh Saxena and Min Sun here did, which is given an image like this, right? This is actually a picture taken on Stanford campus. You can apply that sort of clustering algorithm and group the picture into regions. Let me actually blow that up so that you can see it more clearly. Okay, so in the middle you see the lines sort of grouping the image together, grouping the image into contiguous regions. And what Ashutosh and Min did was they then applied the learning algorithm to say, can we take this clustering and use it to build a model, to build a 3D model of the world. And so, using the clustering, they then had a learning algorithm try to learn what the 3D structure of the world looks like, so that they could come up with a 3D model that you can sort of fly through. Okay. By the way, many people used to think it's not possible to take a single image and build a 3D model. But using a learning algorithm and that sort of clustering algorithm is the first step. They were able to. I'll just show you one more example. I like this because it's a picture of Stanford, of our beautiful Stanford campus. So again, taking the same sort of clustering algorithms, you can, taking the same sort of unsupervised learning algorithm, you can group the pixels into different regions. And using that as a pre-processing step, they eventually built this sort of 3D model of Stanford campus from a single picture. So you can sort of walk into the scene, look around the campus. Okay. This actually turned out to be a mix of supervised and unsupervised learning, but the unsupervised learning, the sort of clustering, was the first step. So it turns out these sorts of unsupervised clustering algorithms are actually routinely used for many different tasks. Things like organizing computing clusters, social network analysis, market segmentation. So if you're a marketer and you want to divide your market into different segments or different groups of people to market to them separately. Even for astronomical data analysis and understanding how galaxies are formed. These are just a sort of small sample of the applications of unsupervised learning algorithms, of clustering algorithms that we'll talk about later in this class. Just one particularly cool example of an unsupervised learning algorithm that I want to tell you about. And to motivate that, I'm going to tell you about consider what's called the cocktail party problem, right? Which is, imagine that you're at some cocktail party and there are lots of people standing all over. And you know how it is, right? If you're at a large party, and everyone's talking, it can be sometimes very hard to hear even the person in front of you. So imagine a large cocktail party with lots of people. So the problem is, if there are all of these people talking, can you separate out the voice of just the person you're interested in talking to, right? Because with all this loud background noise. So I should show you a specific example in a second. But here's a cocktail party that's, I guess, rather sparsely attended by just 2 people. But what we're going to do is we'll put 2 microphones in the room, okay? And so, because the microphones are just at slightly different distances to the 2 people, and the 2 people will be speaking at slightly different volumes, each microphone will pick up an overlapping combination of these 2 people's voices, but they are sort of slightly different overlapping voices. So speaker 1's voice may be more loud on microphone 1, and speaker 2's voice may be louder on microphone 2, whatever. But the question is, given these microphone recordings, can you separate out the original speaker's voices? So I'm going to play you some audio clips that were collected by Taewon Lee at UCSD. Let me actually play for you the original raw microphone recordings from this cocktail party. So this is the microphone 1.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
So it's a fascinating cocktail party with people counting from 1 to 10. This is the second microphone.
1, 2, 3, 4, 5, 6, 7, 8, 9, y 10.
Okay, so remember, in unsupervised learning, we don't know what the right answer is, right? So what we're going to do is take exactly the 2 microphone recordings you just heard and give it to an unsupervised learning algorithm and tell the algorithm, would you please discover structure in the data for me? Or what structure is there in this data? And we actually don't know what the right answer is beginning offhand. So give this data to an unsupervised learning algorithm. And what the algorithm does in this case, it'll discover that this data can actually be explained by 2 independent speakers speaking at the same time. And it can further separate out the two speakers for you. So here's output 1 of the algorithm.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And that was the second output.
1, 2, 3, 4, 5, 6, 7, 8, 9 y 10.
Okay, and so the algorithm discovers that, gee, the structure underlying the data is really that there are two sources of sound, and here they are. Show you one more example. This is this is a second it's a different pair of microphone recordings.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So the poor guy is now at the cocktail party where he's talking to his radio.
1, 2, 3,
There's a second recording.
5, 6, 7, 8, 9, 10.
Right, and if you give this data to the same unsupervised learning algorithm, the algorithm is actually called independent component analysis, and later in this quarter you'll see why. It then outputs the following.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
And that's the second output. Okay, so it turns out that beyond solving the cocktail party problem, this specific class of unsupervised learning algorithms are also applied to a bunch of other problems, like in text processing or understanding functional brain imaging data, like magnetoencephalography and EEG data. And we'll talk about that more when we go and describe ICA, or independent component analysis algorithms, which is what you just saw. And as an aside, this algorithm I just showed you, right, it seems like it must be a pretty complicated algorithm, right? To take these overlapping audio streams and separate them out. It sounds like a pretty complicated thing to do. So you're going to ask, how complicated is it really to implement an algorithm like this? It turns out, if you do it in MATLAB, you can do it in one line of code. So got this from Samuel Wise at Toronto, U of Toronto, and the example I showed you actually used a more complicated ICA algorithm than this, but nonetheless, I guess this is why for this class I'm going to ask you to do most of your programming in MATLAB and Octave, because if you try to implement the same algorithm in C or Java or something, I can tell you from personal painful experience, you end up writing pages of code rather than relatively few lines of code. I should mention that it did take researchers, many years to come up with that one line of code. So this is not easy. So that was unsupervised learning, and then the last of the four major topics I want to tell you about is reinforcement learning. And this refers to problems where you don't do one-shot decision making, right? So for example, in the supervised learning cancer prediction problem, you have a patient come in, you predict that the cancer is malignant or benign, and then based on your prediction, maybe the patient lives or dies, and then that's it, right? So you make a decision, and then there's a consequence. You either got it right or wrong. In reinforcement learning problems, you are usually asked to make a sequence of decisions over time. So for example, this is something that my students and I work on. If I give you the keys to an autonomous helicopter, we actually have this helicopter, here at Stanford. How do you write a program to make it fly, right? You notice that if you make a wrong decision on a helicopter, the consequence of crashing it may not happen until much later. And in fact, usually you need to make a whole sequence of bad decisions to crash a helicopter. But conversely, you also need to make a whole sequence of good decisions in order to fly a helicopter really well. So let me show you some fun videos of learning algorithms flying helicopters. This is a video of our helicopter at Stanford flying using a controller that was learned using a reinforcement learning algorithm. So this was done on the Stanford football field. We'll zoom out the camera in a second. You see the trees planted in the sky. So this is one of the most difficult aerobatic maneuvers flown on any helicopter under computer control, and this controller, which is very hard for a human to sit down and write out, was learned using one of these reinforcement learning algorithms. just a word about that. The basic idea behind the reinforcement learning algorithm is this idea of what's called a reward function. One way to think about it is, imagine you're trying to train a dog. So every time your dog does something good, you say, you know, good dog, and you reward the dog. Every time your dog does something bad, you go, bad dog, right? And hopefully over time, your dog will, you know, learn to do the right things to get more of the positive rewards, to get more of the good dogs, and to get fewer of the bad dogs. So the way we teach helicopter to fly, or any of these robots, is sort of the same thing. Every time the helicopter crashes, we go bad helicopter. And every time it does the right thing, we go good helicopter. And over time, it learns how to control itself so as to get more of these positive rewards. So reinforcement learning is I think of it as a way for you to specify what you want done. So you have to specify what is a good dog and what is a bad dog behavior. And then it's up to the learning algorithm to figure out how to maximize you know, the good dog reward signals and minimize the bad dog punishments. So just to show you, it turns out reinforcement learning is applied, you know, to other problems in robotics. It's applied to things in web crawling and so on. But it's just cool to show videos. So let me just show a bunch of them. This robot was actually, this learning algorithm was actually implemented by our head TA, Zico. Programming a four-legged dog, because Sam Schreiber in this class is also working on the project, and Peter Rebu and Mike and a few others. But I guess this really is a good dog, bad dog, isn't it, since it's a robot dog. Second video on the right, some of the students, I guess Peter, Zico, Tonka, working on a robotic snake. Again, using learning algorithms to teach a snake robot to climb over obstacles. The low left, this is a kind of fun example. Arshad Saxena and Jeff Michaels use learning algorithms to teach a car how to drive at, you know, reasonably high speeds off-road, avoiding obstacles. And on the lower right, there's a robot programmed by PhD student Yirong Shen, you know, to teach sort of somewhat strangely configured robot how to get on top of an obstacle, how to get over an obstacle. Sorry, I know the video is kind of small. I hope you can sort of see it. Okay, so I think all of these are robots that I think are very difficult to hand code a controller for, but using these sorts of learning algorithms, you can, in relatively short order, get a robot to do, you know, often pretty amazing things. Okay, so that was most of what I wanted to say today. Just a couple more last things, but let me just check what questions you have right now. So if there are no questions, I'll just close with two reminders, which are after class today, or as you start to talk with other people in this class, we just encourage you again to start to form project partners, to try to find project partners to do your project with, and also this is a good time to start forming study groups. So either talk to your friends or post in the news group, but just encourage you to try to start to do both of those today. Okay? Form study groups and try to find two other project partners. So thank you. I'm looking forward to teaching this class, and I'll see you in a couple of days.